Hello everyone, I'm Kishan Agarwal. Today I'm going to present my AAT Tech Talk of Cloud Application Development, and my topic is Cloud, Fog or Edge, Where to Compute. This is an important topic in cloud computing. So let us move into the topic. Introduction to Computing Continuum. So what is cloud computing? Centralized data centers that handles large-scale processing but may introduce latency due to distance from data source. That is a very bookish definition of cloud computing, which describes how cloud computing works, which describes cloud computing as a centralized data center, which handles large scale of data for processing, but can implement latency due to the distance of traveling from the servers to the users or the receiver, which requests for the data. So why we are discussing this fog and edge computing. So let us know about that. The advent of fog and edge computing has prompted predictions that they will take over the traditional cloud for information processing and knowledge extraction at a large scale. So the computing continuum extends the high performance cloud data centers with energy efficient and low latency devices close to the data sources located at the edge of the network. However, the heterogeneity of the computing continuum raises multiple challenges related to application management. So this includes a way to offload an application from the cloud to the edge or to meet its computation and communication requirements. To support these decisions, we are going to discuss how the performance and carbon footprint analysis of a selection of use case application with complementary resource requirements across the computing continuum over a real life evaluation test bed. So as we have seen, the advent of fog and edge computing has prompted predictions that they will take over the traditional cloud for information processing and knowledge extraction at a large scale. Notwithstanding the fact that fog and edge computing have undoubtedly large potential, these predictions. So before going to the impacts of fog computing and edge computing, let us discuss what is fog computing and edge computing and how they are different from cloud computing. So fog computing is nothing but a decentralized intermediate layer closer to the data source, balancing performance and latency. So cloud computing has provided like different services such as software as a service, platform as a service, infrastructure as a service, and many other services. But mainly we use these three services by providing different types of cloud such as public cloud, private cloud, hybrid cloud, and other community-based clouds for managing our hardware in a locate or a remote area without worrying about the setup of all the hardware um, instruments or what we say servers all required to set up or working of a software or application for any company or organization. So this is a centralized one. So what does fog computing do is it make it decentralized and act as an intermediate layer closer to the data source, balancing the performance and latency. Latency is the time taken from the request, the this time taken for the request to travel from the user to the server and getting back the response. So this will be decreased by using this decentralized intermediate layer closer to the user or the data source, which will balance the performance and of course latency. So how edge computing works then? Computing at the edge, that means right where data is generated, like IoT devices for minimal latency. So instead of storing all the data generated few hours or few minutes ago from an IoT device to the cloud storage, which is distance apart from the user, instead we are using the nearest servers, or we can say computing at the edge within the city or within the limits, which is more closer than the data centers which are set up apart from that. So to avoid the latency, or we can say minimal latency. So why it is important? The continuum supports applications needing diverse resources and provides low latency, crucial for autonomous vehicles, smart cities, and more. These are the few applications where we are using this type of technology. So we have seen that the fog and edge computing have undoubtedly large potential. These predictions and probably oversimplified and wrongly portray the relation between fog, edge, and cloud computing. So concentrating on fog and edge computing have been introduced as an extension of cloud computing, or not, they are newly discovered. They are the extension of cloud services towards the data sources. Thus we can call them as computing continuum. So the computing continuum enables the creation of a new type of services spanning across distributed infrastructure for autonomous vehicles, smart cities, and content delivery, among other applications which we have already seen. These services have a large spectrum of requirements, burdensome to meet with distant cloud data centers by providing nearest data centers for the storage and access. For instance, they may need low latency connections for fast decision making, making close to a data source, and substantially computing resources for complex data analysis. So the computing continuum provides a vast heterogeneity of computational and communication resources which have the potential to meet these demands. So the heterogeneity of the computing continuum raises multiple applications management challenges, such as way to offload an application from the cloud or the edge. This issue primarily concerns the large diversity of the devices, which range from single board computers such as Raspberry Pis to powerful multiple process servers like quantum computers. This process the following dilemma, such as should we use devices accessible with low latency or with limited resource availability or high performance? These are the multiple questions when we see for the high communication delay. So next, moving to our next slide, which shows the challenges which you have already seen, challenges in the computing continuum. We have seen the heterogeneity. The continuum contains a wide range of devices. Like we have seen a small device from Raspberry to a high powered device like quantum computers. Offloading decisions. Challenges in deciding where the offloaded applications uh, based on latency, resource availability, and environmental impact. Next comes the dilemma, that is whether to use low latency, limited resource devices like edge devices, or using high performance cloud servers with high latency. So to use these edge devices, we have a low latency, but they are limited resource devices. To access these high resources or rich resources, we are going to use cloud servers, but here the latency is increased. So what we are going to do is we are going to discuss the performance and carbon footprint to guide these offloading decisions, which we have discussed. So there comes 3C, or we can say C3, Carinthian Computing Continuum Testbed. So what is this C3 testbed? It is a multi-layer computing platform built for real-world testing, spanning cloud, fog, and edge layers. Like in the diagram, we can see that how here we are taking an example of IoT application. An IoT application which requests these cloud resources, for example, AWS, and we have some fog resources here, and then we have edge resources. So these are all connected to IoT devices and sensors, and the data collection, the process of data collection and manipulation is shown by the arrows. So hosted by the University of Klagenfurt, it uses multiple infrastructure, including AWS, Exoscale, and local resources, which we have seen. At the top level, we have AWS, that is a cloud service, and then we have Exoscale, which includes these fog resources and the SSH. And after that, we have local resources, which uses edge resources like the IoT application sensors and other applications. So what components we require? The cloud environment software used for resource allocation, that is Ascalon, and Mapo. Mapo is a resource provisioning algorithm to help deploy applications across C3. And what is the purpose of it? C3 provides a realistic setting to evaluate performance and environmental impacts across computing layers. So layered architecture of C3. We have seen there are three layers, especially that is cloud layer, fog layer, and edge layer. So cloud layer, high performance, but here comes the latency demand, on-demand resources in centralized data centers with high latency. Use cases, resource intensive task with flexibility, latency requirements. So if we are okay with some high latency, that means time is not so important. So we can use this cloud layer, that is resource intensive task. We require much resources to perform the task. So we need to compromise with the latency. Next comes the fog layer, intermediate layer for low latency applications, like the task where we can locate data sources and data centers to be not too apart. They can be included near to each other so that the application faces low latency. Next, the providers are Exoscale, and we have seen the university which provides private clouds. Next comes our edge layer, computation on site at or near data sources using devices like Raspberry Pi and Jetson Nano. So what are the uses of it? Applications needing immediate response times, example, video streaming or IoT. So which requires very low latency, so that we use this edge layer. Intermediate latency, we use fog layer, and for resource rich task or resource intensive task can be achieved using the cloud layer, which requires a high latency. So we have discussed the three layers of C3 by their latency, or we can say accessing speed. So benchmark application evaluator. So we'll see what is the overview application of this study of C3, which we have discussed, the layers and all. So the study evaluates three types of applications, each with unique resource needs and environmental impacts. So we are going to see the carbon footprint or the environmental impact that these layers have. So first is video encoding, that is high computational demand used for streaming and content delivery. These are the real-time applications of video encoding. Next is our machine learning, high memory, which requires high memory and processing needs. So used in automation and data-driven decisions, like predicting what price of an on-demand product, or performing market-based analysis or different scenarios, which requires machine learning, processing of machine learning algorithms by using a large amount of data stored or collected from the different customers in different seasons or different occasions. Next is in-memory analytics, fast data processing for real-time insights, example, recommendation systems. So that is not using cloud resources, the available resources near the data users, that is in-memory analytics. So these are the three applications which we have seen. So what goal we can observe is how these applications perform across different layers and their carbon footprints. So we'll discuss that. So first comes our video encoding. So we'll discuss the performance evaluation of this video encoding. So this is tested on HD, Full HD, and Quad HD resolutions. So what we have seen is, like, see, we have evaluated using FFmpeg MPEG on various devices in C3, that is layered structure. So what were the results? Edge devices such as Raspberry Pi, Jetson Nano, which we have already discussed, the edge devices are good for video on demand with faster encoding and lower transfer time. That is, the processing time is also high and the latency is also very low. Next, the cloud resources suitable for live streaming due to low encoding time. So recommendations, usage of edge for on-demand cloud for live streaming, depending on transfer and encoding time balance. So edge devices are useful in this video encoding. And next comes our machine learning evaluation. So why, what were the performance analytics or evaluation for machine learning? So they are tested on two networks, that is quantum neural network and convolutional neural network. So quantum neural network, which requires low training time limited to small data sets, whereas convolutional neural network CNN, which requires more complex tasks to be performed and require high memory and computation. That means it is resource intensive task. So what were the results on these two networks? Edge devices, which we have already discussed, are suitable for lighter models or smaller data sets such as quantum neural networks, whereas this cloud and fog resources can handle large data sets and complex models better, like CNN. So based on the type of network we are using, which requires small data sets or large data sets, we can decide which type of devices we can use or resources we can use, like edge, cloud, or fog. That's all. Use edge for smaller ML models and cloud or fog for extensive ML, because these large data sets require complex computational task and which requires resources, more resources, or we can say resource intensive task. The last one is memory, in-memory data analytics. So what were the performance of it? To use two use cases like collaborative filtering, that is recommendations, and pi estimation, that is intensive computations. So what were the results? Cloud and fog perform best on memory intensive tasks due to higher memory and faster processing, whereas edge may handle smaller, less intensive data analytics tasks. So what is the recommendation? Same. If we require high memory task, go for cloud. If we require moderate workload, go for fog, or which requires very low or small type of processing, you can go for this edge. So by observing these three types of performance evaluation, we can see that whenever we require high computational resources or resource intensive tasks to be performed, we can go for cloud devices or cloud applications. So for intermediate type of thing, we can go for fog, and for less or quicker performance or time where time matters more, we can use edge type of devices. So we'll see the network performance evaluation. Network tested downlink, throughput, and latency. These are the three things. So what were the results? Edge devices provides high throughput and lowest latency, which we already know, ideal for frequent data exchanges, whereas cloud and fog will be advocate for large data, but it's higher latency based on the distance uh, required to access this all. Recommendations. Same. Favor edge or fog for applications with frequent data input or output. But if you are not with that, suitable with less latency tolerable, that means the time for the evaluation doesn't matter, then you can go for the cloud. Let's discuss about the environmental impact, that is carbon footprints or carbon emissions. So in this testing, we have evaluated power consumption during ML task and calculated CO2 emissions. So what will the results is, edge devices emit up to 6 times less carbon dioxide than cloud or fog devices. That means which requires less resources, and also obviously we can say that it will emit less carbon dioxide. So for small or small scale applications, we can use edge devices so that the environmental impact will also be reduced, unnecessarily going for cloud or fog devices. That's what the recommendation is. Offload applications with soft performance constraints the edge to reduce the carbon footprints. So we'll discuss what we have already discussed in these scenarios. So summarizing the ideal offloading for each application. See, video encoding, we can go for edge or fog for on-demand, cloud for live. Machine learning, same, edge for small data sets, which we have already discussed, quantum neural networks, and cloud or fog for complex models such as CNN. And in-memory analytics, cloud or fog for high memory needs and edge for low. So environmental considerations, we have seen that edge computing or edge tools reduces carbon dioxide emission by 6 times something lesser than the cloud or fog, so which are suitable for applications. C3 offers insights into effective offloading across cloud, fog, and edge layers, which we already seen the 3-layer system, and the tailor offloading to application requirements to optimize performance and environmental impact. So these are the best practices to reduce environmental impact as well as reducing your latency, performance improvement, and all based on the C3 layer which we have discussed. Thank you.